Yesterday I reviewed a demo where a 7 billion parameter language model ran on a single RTX 3080 with latency comparable to a full precision model on a cloud-grade GPU. The only change was that the model had been quantized to 4 bits using a recent GPTQ-style algorithm. This illustrates a shift. Quantization is no longer an experimental trick but a practical tool that can have memory usage and double inference speed without obvious quality loss. For many teams, the cost of moving a model from research to production is dominated by GPU memory and electricity, so a 2x reduction in memory directly lowers cloud bills and enables real-time use cases that were previously out of reach. Quantization reduces the numeric precision of a neural network's weights and activations, typically from 16-bit floating point to 8-bit integer or lower. Static quantization fixes a scale per tensor, while dynamic quantization determines scales at runtime, trading speed for flexibility. Recent research, such as GPTQ, Detmers et al. 2023 and SmoothQuant, Lin et al. 2023, shows that careful per-channel scaling and error-aware rounding can preserve model quality even at 4-bit precision. The process usually involves a calibration dataset to capture activation statistics, followed by a fine-tuning step that corrects any drift. Because quantization operates on the model parameters themselves, it does not require changes to the underlying hardware, though support for low-bit arithmetic in GPUs or accelerators improves the speed gains. The key impact of recent quantization advances is a reshaped performance cost curve. By compressing weights to 4-bit or even 3-bit, memory footprint shrink by 75% or more, allowing larger models to fit on a single GPU that previously required multi-GPU sharding. Benchmarks from the DeepSpeed team, 2024, report that a 4-bit Llama 7b model runs at 2.3 multiplikationszeichen the throughput of its FP16 counterpart on an A100, while perplexity degrades by less than 0.4%. Similarly, GPTQ-based quantization of a 13 billion parameter model achieves near FP16 quality with a 60% reduction in latency on consumer-grade hardware. These results mean that the marginal cost of adding capacity is lower, and the decision point between cloud-scale deployment and edge inference moves toward the latter. 2 practical insights emerge. First, the benefit of low-bit quantization depends heavily on hardware support. GPUs with native INT4 kernels, such as the NVIDIA H100, deliver the full speedup, whereas older cards fall back to emulation and see modest gains. Second, quantization does not eliminate all accuracy gaps. Certain token-sensitive tasks, like code generation, still lose up to 5% BLEU score at 3-bit, highlighting a ceiling for aggressive compression. Finally, many developers assume that quantized models can be swapped into existing pipelines without change, but quantization can interact with mixed precision training and with retrieval-augmented generation, requiring careful validation. Recognizing these limits prevents over-promising performance in production. In summary, recent quantization techniques compress large language models enough to change the economics of inference. Memory savings allow bigger models on cheaper hardware, and the modest accuracy trade-offs are often acceptable for many applications. However, the actual gains are bounded by hardware capabilities and by task-specific sensitivity to low precision. Practitioners should benchmark quantized models on their target stack, verify downstream quality, and stay aware of emerging kernel support. Our channel aims to keep you informed without hype, so you can make grounded decisions about model deployment. If you found this analysis useful, consider subscribing to the Latent Dispatch for regular, source-driven updates on AI research and deployment trends.